Hi, I'm Dr. De Bruin, and this is another A-level chemistry exam question walkthrough from the electrochemistry topic. Let's get started. A lot of students tell me that electrochemistry is their least favourite topic, and that's partly because it is tricky, but it's also because there are a number of questions where those students genuinely do understand the chemistry, but the answer has to be given in a certain format or in a certain way, and so even though they understand the chemistry, they find themselves losing out on marks. And the first part of this question is a classic example of that type of question. So this style of question is quite tricky, but it's also very common. And in it, we're asked, why can one species reduce another species to a certain oxidation state, but not all the way to zero? So here we're asked to explain why lead can reduce an aqueous solution of tin 4 plus ions to tin 2 plus ions, but not any further. So why can't that lead reduce tin all the way back to its elemental form? So firstly, we're going to need to look at the data in the table. And we can see here that we've got positive 0.15 for the reduction potential for tin 4 plus, and then negative 0.13 for lead 2 plus. So what a lot of students would say to me at that point is, okay, so I can see that lead has got the more negative reduction potential, therefore that equation is the one that's going to flip over and go in the opposite direction. And their understanding is absolutely bang on, but unfortunately we can't write it quite like that in the exam. So what are we going to write? Well, the first thing we're going to say is that the potential for tin 4 plus is greater than the potential for lead 2 plus. You could also write this in terms of it is more positive, but the crucial thing here is that we need that the E value for that particular species, giving the formula of the ion, is more positive than or is greater than. Now, some people choose to write both parts, both of the species that are in that half cell, and you absolutely can do that, but you don't have to do that. So I tend to skip it and just name the thing that is on the left of the equation. Now, the other way that you could phrase this for the same first mark is you could talk about what the electromotive force would be if those two half cells were joined together. So here we could say that the electromotive force of the reaction between tin 4 plus and lead, so if we had flipped that second equation over, would be plus 0.28. In other words, we would get a positive potential difference, and therefore this reaction would happen spontaneously. Then we need to look at the second part of the question, which is why can't it reduce it any further? Why can't lead reduce tin 4 plus ions all the way back to tin metal? So if we have a little look here, we can see that the potential for tin 2 plus is less, it's lower than the potential for lead 2 plus. And again, we could put the both of the species in those half cells in there. Now, looking at the EMFs here, people can start to get a little bit confused. So let's look at these numbers. So here, the tin 2 plus is going to be going in the forward direction, and the lead 2 plus is going to be going in the reverse direction. And that's going to confuse a lot of people, because what you've probably been taught is whatever the more negative value is, that's the equation you flip over. And if we're trying to figure out what the spontaneous reaction would be, that's true. But we're not being asked here what's the spontaneous reaction, we're being asked why it can't happen in a particular direction. So we need it to be going in that direction. And the direction we're being asked to look at is the direction where tin 2 plus is reduced to tin with an oxidation state of 0. So that one is going forwards. So if we were to do that, then we'd be doing minus 0.14, take away negative 0.13. Or you could do flipping the sign and adding it on, either one works out. And so therefore we'd be getting an electromotive force that is minus 0.01. So what that tells us is because that value is negative, that reaction will not happen spontaneously. That reaction will not occur. Next, we're asked to identify a species that can reduce tin 4 plus all the way to tin metal. So here we need to look at our table, and we need to look for a value that is more negative than both of the tin electrode potentials. And the only one that we've got in there is that minus 0.44. So obviously the substance that's going to reduce the tin is going to be the one that is on the right hand side. So that there is going to be iron, and I'm going to write the symbol for iron and write the solid after it to make it very clear that I mean iron metal. I don't mean iron 2 plus or iron 3 plus or any other species that's related to iron. And then lastly, we've got a 3-part question talking about an electrochemical cell where we've wired together a half cell that contains tin 4+ and tin 2+, and then another half cell that's got these manganate ions and also manganese ions. So firstly, we're going to calculate the electromotive force of this cell. So that's nice and straightforward. We know that the manganese-based reaction is going to go in the forwards direction because it's the more positive value, and the tin-based reaction is going to go in the reverse direction because that's the less positive value. So therefore we're going to be doing plus 1.51 plus negative 0.15 because I've flipped that one over, which gives me a value of plus 1.36 volts. Next, we need to give the conventional representation. So I'm going to start off by identifying that both of these half cells are redox half cells. They don't have a solid metal associated with them. So I'm going to need some platinum electrodes either side. And you can see I've got my phase boundaries there and also my salt bridge in the middle. Next, I need to think about which is going to go on which side of the reaction. So the reaction that is going in the forward direction, that's written in the same way that it is in the table of electropotentials, is going on the right-hand side. So that's going to be my manganese side, and my tin is going to be on the left. And then I need to make sure that for each side of the conventional representation, the more oxidized species is nearer to the salt bridge. So on the left, that's going to be manganate nearer to the salt bridge because that's got an oxidation state of +7, and then manganese on the right. And I've got a comma between those because they are in the same phase. They're both aqueous solutions. And also, if I want to include my hydrogen ions, then they're going to go here next to the manganate ion. Now that confuses a lot of people because you've just kind of been taught to think about what's the oxidation state, but we're not thinking about what the oxidation state of the hydrogen is, because obviously in that case it would go on the right hand side. If you look at where those hydrogen ions have come from, they've come from the same side of the equation as the manganate ion, so you keep it together with the manganate ion. And then on the left-hand side, we're going to have our tin 4+ nearest to the salt bridge because it's more oxidized. It's got an oxidation state of +4, and then the tin 2+ to the left. And then finally, we've been asked to give a half equation for the reaction that occurs at the negative electrode. So think about why that electrode is negative. This isn't electrolysis. It's not giving up electrons. It's negative because something is giving it electrons. So we need to think which half equation is giving up electrons, and the answer is that it's going to be our tin. That's the reaction that's going to be giving up electrons, and so obviously this is the one that's been flipped over, so it's not a reduction potential as it was given in the table anymore. It's now written as an oxidation potential, and so we've got our tin 2+ splitting apart to make tin 4+ and 2 electrons. Thanks very much for watching, and I hope you're finding it useful to walk through some exam questions with me. If you are, then don't forget to like, subscribe, comment and tell me which topics to cover next, and also share the channel, and I'll be back soon with some more A-level chemistry.